In the crushing pressure of the deep ocean, light is useless and sight is a liability. To survive, odontocetes evolved biological hardware, so advanced it puts our best sonar to shame. Today, we're dissecting the acoustic lens of the Melon to reveal the biophysical geometry behind underwater vision. Water actively absorbs the electromagnetic spectrum. Sunlight dissipates completely within the first few hundred meters of the ocean surface. Acoustic waves, however, encounter minimal resistance, traveling through water nearly 5 times faster and over much greater distances than they do in air. Odontocetes, the toothed whales, including sperm whales, dolphins, and porpoises, capitalized on this physical reality. They abandoned optical reliance to become apex acoustic masters. Their cranium evolved away from the standard mammalian blueprint, reorganizing into a highly integrated, distinctly asymmetrical acoustic transmitter and receiver. Surviving and hunting in total darkness requires replacing the traditional eye with pure biophysical geometry. This schematic reveals the 3 core hardware components we need to dissect: a pneumatic generator, a refractive acoustic lens, and an isolated receiver. First, the dorsal nasal passages, situated near the blowhole, serve as the primary site of sound generation. Second, the forehead melon sits directly anterior to this generator, functioning as an internal acoustic lens to focus and collimate the outgoing sound. Finally, the lower mandible operates as an isolated receiving antenna for capturing returning echoes. Completely decoupling the transmission hardware from the reception hardware allows the animal to generate, focus, and receive high-intensity ultrasound simultaneously within a single skull. The engine of this system lies in the dorsal aspect of the nasal passages, at a specialized valvular structure known as the phonic lips. To generate an echolocation click, the animal pressurizes air and forces it across these overlapping fleshy flaps. The extreme pressure differential induces high-frequency vibrations, self-sustained vibrations in the surrounding fatty tissue, called the dorsal bursae. Empirical data from electromyography and contact hydrophones confirms a strict asymmetry in this process. The right dorsal bursa acts as the primary generator for these clicks. Generating this kind of pneumatic pressure continuously during a deep dive presents an immediate logistical problem. Exhaling air to create sound would normally deplete the animal's oxygen supply at depth. Instead, the anatomy features a closed-loop recycling system. Air forced past the phonic lips is captured in paired accessory vestibular sacs and routed back into the lower nasal passages, preserving the finite air supply. The immediate output of this vibration is a brief, highly energetic, broadband pulse that can reach frequencies up to 200 kHz. But in this raw state, the pulse is entirely unfocused. Without an organizing mechanism, this acoustic energy would scatter 360 degrees into the surrounding skull and water. A scattered signal degrades instantly, rendering it useless for long-range navigation. To solve the scattering problem, the pulse travels forward into the melon, the massive structure sitting directly anterior to the phonic lips. The melon consists of a 70 to 80% matrix of specialized triacylglycerols and unusual branch-chain wax esters. These 2D parasagittal CT scans measure tissue density, revealing a deliberate internal density gradient. The outer shell consists of denser tissue with a high concentration of collagen fibers. Moving inward, the tissue transitions into a low-density core, exceptionally rich in oily lipids. This animated diagram translates that physical density into a radial sound speed gradient. Sound travels faster through the dense periphery and slower through the oily core. When the unfocused sound waves enter the rear of this gradient, they interact with these varying velocities. Following the physics of acoustic refraction, the outer edges of the wave accelerate through the dense shell, forcing the entire wavefront to bend inward toward the central axis. This phenomenon is known as collimation. The fat physically narrows the expanding wave into a directional, 3-dimensional bio-sonar beam, reducing the beam width to 10 degrees. Through evolutionary biochemistry, the odontocete relies on lipid topography to physically refract a chaotic sound wave into a targeted acoustic laser. Even with a perfectly collimated beam, the outgoing transmission faces one final hurdle: the boundary interface between the animal's biological tissue and the open ocean. When an acoustic wave hits a boundary between two materials with distinctly different densities, a large percentage of that sound reflects and scatters backward. This animated split screen illustrates the solution: acoustic impedance matching. The lipid composition of the outer melon calibrates its density to roughly 950 kilograms per cubic meter, aligning with seawater. This matching prevents the boundary from acting as a wall, allowing over 90% of the acoustic energy to transmit into the environment with minimal backscatter. Maximizing energy transfer ensures the echolocation beam retains its amplitude, penetrating deep into the abyss. Once the pulse leaves the head, it strikes a target: a squid, a fish, or the seafloor. Microacoustic reflections instantly return toward the animal. Odontocetes do not capture these echoes with external ears. The ear canals are vestigial and plugged. Instead, they receive their returning sonar directly through their lower jaw. Looking at these 3D cranial reconstructions, we locate specialized lipid deposits called intramandibular fat bodies, resting inside the hollowed-out lower jawbone. These acoustic fats have an impedance identical to seawater, allowing them to act as a sensitive receiving funnel that captures returning microvibrations straight out of the water column. Once captured, this bone and lipid conduction pathway channels the high-resolution vibrations directly backward into the tympanoperiotic complex, the dense bony housing of the middle and inner ear. This completes the hardware loop, highlighting the mechanical necessity of spatial decoupling between the dorsal transmitter and the ventral receiver. Physical isolation ensures the massive 200 kHz outgoing blast from the melon does not instantly deafen the animal to the faint echoes returning to its jaw. When we pull back from the anatomy and view the entire hardware loop functioning in the open ocean, the scale of this biophysical achievement becomes clear. The auditory cortex operates as a high-speed biocomputer. By measuring the exact millisecond time delay between the outgoing click and the returning echo, the animal calculates precise distances to targets hundreds of meters away. By simultaneously analyzing micro-Doppler frequency shifts in those returning echoes, the brain extracts the exact velocity and directional heading of moving prey. The continuous processing of these thousands of clicks per second results in a high-fidelity, three-dimensional spatial rendering of the environment. The odontocete brain plots the internal density, speed, and geometric shape of its reality in absolute darkness. Human engineering is now attempting to catch up, working to reverse engineer this biological framework. Current biomimetic sonar research focuses on replicating the melon's lipid topography. Engineers are testing synthetic acoustic lenses for autonomous underwater vehicles, utilizing artificial density gradients to focus sound precisely as the animal does. Perfecting these synthetic refractive lenses is the necessary next step for deep-sea exploration. The asymmetric odontocete skull serves as a refined biological solution for high-frequency acoustic projection. Dive deeper into the forces that shape our reality. Click the subscribe button, activate the bell, and see you in the next scientific investigation, Beyond the Boundaries of Reason, only on TEMBODocs.